Okay, let's continue with our finding our limits. So these are the types of problems you'll find on MyMathLab. Notice what happens. I try to stick 2 in. That's always your first defense, guys. Just put this in. Well, that gives me 0 on the bottom. Fantastic. I can't have that. So let's fool around a little bit with this numerator. I can factor that into, what's that factor into? X minus 2, x plus 3. Okay, so factor that quadratic, and notice what happens. The x minus 2's cancel. So I end up with the limit as x approaches 2, really of just x plus 3. Okay, factor the numerator, and this is what you get. So now I can put 2 in. Now I can go ahead and put 2 in for x. 2 plus 3 equals 5. So the limit as x approaches 2 of this function, even though it never is going to, I can't actually put 2 in and get 5, the limit gets close to 5. Okay, the y value gets close to 5. There's a big fat hole there, but that's the limit. The limit does exist, and it's 5. This one I can't really factor, but we use a strategy that we use in algebra called multiply by the conjugate, right? To get that kind of play with square roots and get rid of the fact that I have a square root. We're going to multiply by the conjugate. Okay, and anytime I multiply a fraction by something, I multiply the top and the bottom by the same thing, right? So that I'm really just multiplying by a 1. So I have square root of x plus 2 over square root of x plus 2. When I FOIL the top, I get x plus square root of 2x minus square root of 2x. That cancels, or that adds to 0. And then negative 2 times 2 is 4. So I have the limit as x approaches 4 of x minus 4 over, now I am just simply, I'm not actually going to do this multiplication. I'm just going to write the two terms beside each other, the two factors beside each other. I did the foiling up here because I used the conjugate so I could get rid of things. Okay, once I did that, I'm just going to multiply the bottoms together because the reason I did this was to get this x minus 4 term. You know, x minus 4 over x minus 4 is just 1. So I have 1 over the square root of x plus 2. Well, now I can put 4 in. When I put 4 in there, I get 1 over the square root of 4 plus 2. 1 over 2 plus 2, that's 1/4. So the limit as x approaches 4 of this function is 1/4. Even though I can't put 4 in. Look, I put 4 in. 4 minus 4 is 0. I can't have 0 on the bottom. So I manipulated my equation to find out where this hole was that I'm getting close to. I'm getting close to 1/4, even though I never actually hit 1/4. Okay. This bottom one, ooh, a little tough here to see what to do. Anytime you see a quadratic, I hope it kind of, you might think, well, it's a quadratic. Let's factor it and see if that leads me anywhere. It's always a good line of defense there to factor. What is that? X minus 1, x minus 1. So it gives me x minus 1 squared over x minus 1 cubed. Well, that's just 1 over x minus 1. Now I'll put 1 in. I still can't. 1 over 1 minus 1, that's 1 over 0. It's looking like this one maybe doesn't exist. So I might graph it, see what's happening, or like we did in the beginning in 3-1 part 1, put something really close to 1 in. Let's put 0.999 in. And then let's also put 1.0001 in. Okay, you have stuff that's getting close to 1 on each side. What you'll find is that as I approach from the right, okay, 1.001, I get really big numbers close to infinity. And as I approach from the left, I approach negative infinity. Therefore, what we suspected is true. This one does not exist. Okay. So at first glance, don't just put the 2 in and be like, oh, I get 0 on the bottom. It doesn't exist. It could just be a hole in the graph, which means it's still getting close to something, even though it doesn't actually touch it. Okay, and then the limit does exist, so be careful. Suppose a small pond normally contains 12 units of dissolved oxygen in a fixed volume of water. Suppose also that at time 0, a quantity of organic waste is introduced into the pond, with the oxygen concentration T weeks later given by this formula. As time goes on, what will the ultimate concentration of oxygen be? Will it return to 12 units? Okay, so this is where limits are used in real life, okay? In other words, we want the limit as time approaches infinity. It says as time goes on. Okay, so we've had the answer be infinity, but we've never had our variable be approaching infinity. As time gets huge, does that come back to 12? Is that going to just be 12 units? Let me show you what the graph looks like here. This is the graph of that function. And notice what we did. We let time be 10, 100, 1,000, 10,000, 100,000. What's happening as time gets close to infinity? It looks like, look what's happening to our y-coordinate. It was 11.85, 11.985, 11.9985, 11.99985. It's getting closer and closer to 12. 12 is a horizontal asymptote. The oxygen concentration will approach 12, but will never be exactly 12. But the limit as time goes to infinity is 12. Okay? We saw it with a graph. And there's ways to do that, though, with algebra, which we'll show you. And it comes from this fact. This is the graph of y equals x squared. Or I'm sorry, 1 over x squared. It's the blue graph. We know what 1 over x looks like. That's the red graph. Okay? 1 over x squared is the blue graph. And what we notice is that no matter what, as x gets closer and closer to infinity, look what the y coordinates get close to. They get close to 0. Whether it's just 1 over x or 1 over x to a power, it's going to be getting close to this 0 asymptote. Okay, so the limit as x approaches infinity of 1 over x to the something gets really close to 0. And we're going to use that for this problem that we saw on the previous page. We did this before, and we saw the graph. We know it approaches 12, and now I just want to show you why. What we're going to do is divide every single term by the biggest power of the exponent. So we're going to divide everything by t squared. Okay, 12t squared over t squared, 15t over t squared, 12 over t squared, everything over t squared. Notice the t squareds will cancel here. Here this will go away and this becomes a 1. This cancels to 1. That's about all we can do, giving us this. Okay, so what we're going to do now is use that fact that the limit as t approaches infinity of this is 0, and this is 0, and the 1 over t squared is 0. Okay, that's all of these terms are going to go to 0 because of that theorem we had on the other page. Okay, sorry, I guess I have that on the next page. Okay. So, for example, we're going to take the limit of 12. We're going to take the limit as t approaches infinity of this. The limit as t approaches infinity of that. That's what all those properties allow us to do. We can take it through there. So this gives me just 12 because everything else, anything that has a t on the bottom still, disappears. And so the limit is 12. Okay, so to find limits at infinity, that's a procedure that we use. We just divide by the highest power of x in the denominator. And then we use the rule that any limit as x approaches infinity is 0, and the limit as x approaches negative infinity of 1 over x to the n is also 0. Okay, so for these, what we'll find as we do these then, the biggest power of x is x. So I'm going to take 8x over x, 6 over x, 3x over x, and 1 over x. The x's cancel here, so I have 8 plus 6 over x over 3 minus 1 over x. Of course, it's the limit as x approaches infinity of this. And then because I can take the limit of each of these terms, all 4 of these terms, this one goes to 0. The limit of that is 0. My final answer is just 8/3. That's the horizontal asymptote, is 8/3. Okay. In this next one, we try to do the same thing here. Biggest power is x cubed. So I am going to take 3x over x cubed, 2 over x cubed, 4x cubed over x cubed, and 1 over x cubed. That's going to give me the limit as x approaches infinity. That'll be 3 over x squared. Nothing I can do with this one. 4, that becomes 4. Okay, and then I'm going to take the limit as x approaches infinity of each one of these. This goes to 0, this goes to 0, and this goes to 0. So I get 0 over 4, which is 0. So the limit as x approaches infinity of this is 0. In this next one, I'm going to divide everything by x. That's the biggest power in the denominator. Okay. So then I get the limit as x approaches infinity. What's that? 3x plus 2 over x all over 4 minus 3 over x. Okay, so now this goes to 0 and this goes to 0. But as x gets huge, I get 3 times a huge number over 4, right? 3 times a huge number over 4. So what is happening to that? The limit as x approaches infinity of that is just infinity. Okay, right? As x gets huge, this whole thing gets huge. Alrighty. Let's try this one down here. I'm trying to show you all different things that happen. The biggest power is x squared. Okay, for this one. So I'm going to divide the biggest power of the denominator. I'm sorry, I'm not writing the limit. I really should be. Just don't have enough room. I'm dividing by the biggest power in the denominator. And I'm taking the limit of each. What was it? Yeah, x squared minus 1 over x squared. So that gives me 5 minus 4x over 3 plus 2 over x minus 1 over x squared. So the only thing that zeroes out here are these two. So I get 5 minus 4x over 3. Now I want you to think about what's happening. 5 minus 4x over 3. 5 minus 4x over 3. The limit as x approaches infinity of 5 minus 4x over 3. If x is getting huge, like 10,000, 5 minus 40,000, isn't this going to be a negative number, right? 5 minus 40,000 over 3, 5 minus 400,000 over 3. Be careful whether you're getting infinity or negative infinity. Don't assume it's infinity. Think about whether it's infinity or negative infinity. Okay? All right. That's everything. Good luck.